There's a story I want to tell you. I was given a physics lecture on the buoyant force and what determines whether something sinks or floats. And so I gave a worked example on the whiteboard where I had a boat and I said that there was a party on the boat and that more and more people kept getting on the boat to go to the party. And so the question was, how many people would get on the boat before the boat sunk to a level where the people started to get their feet wet? And so that was the work example that I gave. And then on the next exam, to test this concept of buoyancy and sinking versus floating, I gave a problem where there was an iceberg and there were more and more penguins getting on the iceberg. And the question was, how many penguins need to get on the iceberg before they get their feet wet? So I'm hoping that some of you can see the relationship between those two different examples. But here was the thing. There were a lot of students that were frustrated with me because they said, we've seen you work through lots of examples and we never saw anything that dealt with an iceberg or dealt with penguins. And so what's happening here is an inability to what is called transfer learning. So usually when you learn something for the first time, you learn it in a particular context. And so the idea of transfer is to be able to take what you've learned in one context and transfer it to a novel context. Okay, so learning about the buoyant force and whether things sink or float in the context of a boat and humans, there's deeper underlying structure in your understanding of that problem than if it's humans and the boat. Okay, that is a surface feature of the problem. The humans are a surface feature. The boat is a surface feature, just like the penguins are a surface feature and the iceberg is a surface feature. There's deeper underlying structure between understanding the concepts beneath the more superficial surface structure. And so this is the key to being able to transfer, is that you understand a more deep underlying structure behind how to solve problems that go beyond the mere surface features. And so the question becomes, okay, well then how do you develop the ability to do that? The way that you develop the ability to do that is you have to have multiple opportunities to compare and contrast different kinds of problems. And this is yet another reason why I'm so big on having lots and lots and lots of practice solving problems, because the more problems you solve, the more contrasting cases you have, and the more contrasts you make, the more you are able to differentiate what might be ostensibly similarities or differences based on the surface features of a problem versus the deeper underlying structure and whether or not different problems have that in common. So, for example, there are problems that might ostensibly look very different, but they actually have very similar solution strategies. So, for example, we've talked about energy conservation and we've talked about conservative forces. And when the only forces acting in a situation are conservative, we can say that the total kinetic energy plus the total potential energy is going to remain constant. Now, how much of its potential and how much of its kinetic can slosh around, but overall it remains constant. So, for example, if you were given a problem where there was, say, a roller coaster and you were told to ignore friction, ignore air resistance, and it's essentially a roller coaster car that's going up and down and up and down. And so it has kinetic energy, but then it also has, at different heights, different gravitational potential energy. So you could solve that problem with a conservation of energy approach. Now, another problem might be a cart that's attached to a spring that's oscillating from side to side. Now, a spring might not look a lot like a roller coaster, but I'll tell you what, it's a very, very similar solution strategy. Now, the conservative force is the elastic force of the spring. It's a restoring force as well, just like gravity is. And once again, you can set the problem up by saying that the kinetic energy plus potential energy before equals the kinetic energy plus the potential energy after. So even though the surface features of these two problems are ostensibly different, there's actually a very similar underlying structure. This has been studied, and when it comes to learning, lots of studies have been done to try to look at what makes experts experts in their particular fields. Because if we have an understanding of like what makes an expert, that gives us a sense of the kinds of things we want to support in learning environments so that people can learn things more deeply. Because in theory, experts have learned things more deeply than novices. With respect to physics, for instance, there's been cases where you'll have both physics experts and physics novices, and then you'll give both groups these various different problems, and then you'll ask them, okay, well, which problems do you think are similar? And so, for example, a expert physicist would be able to see that, say, a roller coaster problem and a spring problem, even though they ostensibly look different at the surface, actually have a deeper underlying structure that's in common, i.e. conservation of energy. Meanwhile, the novices, they would look for the surface features. So for instance, they would lump together problems that had inclined planes, for example, or they would lump together problems that had springs. Okay, so the idea here is that when you're just noticing the surface features, there's more to notice. There's deeper underlying structure. And the way to begin to grasp that deeper underlying structure is to contrast cases. And in this case, it means solving more and more and more problems. The more problems you solve, the more similarities and differences you'll see in these problems that go deeper than just the surface features of the problems. And so the hope would be that eventually you have a more elaborate way of organizing your knowledge about physics, which is to say that when you're presented problems, you're thinking through your head, is this, say, an energy conservation approach? Or is this, say, a momentum conservation approach? Which is different than being at the surface feature level of things where when you're presented problems, you're thinking to yourself, oh, this is a spring problem. Oh, this is an inclined plane problem. Oh, this is a problem with a pulley. Oh, this is a problem with a string. You see the difference there? When you're organizing your understanding by the surface features, you're overlooking the deeper underlying structure, because things that are ostensibly different, like, say, humans getting on a boat versus penguins getting on an iceberg, actually have very similar underlying structure. And when you get more and more into the underlying structure, that gives you a better and better chance of transferring your knowledge, i.e. transferring your knowledge about sinking and floating with people getting on a boat and transferring it to penguins getting on an iceberg.